In this video, we begin an exploration of something called colligative properties. Colligative properties are a collection of the properties of a mixture that only depend on how much solute you have dissolved in a solvent and not on the type of solute that you're mixing with the solvent. We have already seen one colligative property, and that is the vapor pressure depression when you add a solute to a solvent. Okay, when we were introducing Raoult's law, we saw that that law essentially tells you what is the vapor pressure of the gas at equilibrium with the liquid when you start to add different component to that mixture, a little bit of solute to that mixture. Okay, so Raoult's law is actually a colligative property because, again, it tells you how the property of the solvent changes when you add solute. And the way that it changes is like this. The vapor pressure of that solvent is equal to the mole fraction of the solvent times the vapor pressure of that solvent when pure. Now we can express this as a function of the solute as opposed to the solvent, and that just simply turns into this. If you have a binary mixture with only two components, A and B, okay, and again, it tells you what is the effect of a solute on a property of the solvent. That's what a colligative property is. And notice that it doesn't matter what B is, it can be any substance that you want, okay, that is going to affect the same way the property of the solvent as long as the concentration is the same. Again, so colligative properties, they only depend on the concentration of the solute, not on the chemical nature of the solute. Okay, in this video we're going to see two new colligative properties, which are the freezing point depression of the solvent and a boiling point elevation of the solvent. And in the next video we'll see osmotic pressure, which is another colligative property. Alright, so let's try to see the story behind the boiling point elevation and freezing point depression of a solvent. Last chapter, when we were studying pure substances, we learned about graphs that told us how the molar Gibbs energy of a pure substance changed with temperature. Okay? Remember that this equation came from the first derivative of the molar Gibbs energy with respect to temperature at constant pressure. Okay? And that is the minus molar entropy of each one of the phases. The way that these graphs look like were like this. That's the line of the solid, this is the line of the liquid, and that's the line of the gas. Okay? Now these lines allowed us to figure out what the freezing point and boiling points of that particular substance were. Okay, as we have right here. Alright, now we're going to use this knowledge, but instead of using here a pure substance, we're going to add a solute to this substance. Okay, so we're going to be in the liquid phase and going to add a little bit of solute to that solvent. Okay, now instead of using molar Gibbs energy, what we actually use is the chemical potential. So that will be the chemical potential of my solvent A. Okay, and this will be just the freezing point and the boiling point of that solvent. Now, the way that we're actually going to do this explanation is by assuming that the solute that I'm adding, okay, I have here my liquid, and I'm adding a solute B, and it could be anything. It could be, if this is water, it perhaps could be ethanol or glucose or sucrose. Okay. What I'm going to assume is that the solute that I'm adding is non-volatile and non-freezing. That means that when I take this mixture and I bring it to the boiling point, only the solvent is going to go into the gas phase. And when I freeze this, only the solvent is going to freeze. Okay, the solute will stay in solution. Okay? Well, if that's the case, then what happens is that, notice that the lines of the solid and the lines of the gas would not change when I have the solute, because again, the solute does not go into the gas phase or does not mix with the solvent in the gas phase or in the solid phase. Only the line of the liquid is affected. And then the question is, well, how is the line of the liquid affected? Well, we can see how the variation of the chemical potential of A is affected by the presence of a solute, because we know how to write the chemical potentials as a function of concentration. Okay? This will be the case of an ideal dilute solution, in which I'm simply mixing just a little bit of solute in a majority solvent component. Okay, and we know how to write the chemical potential for an ideal dilute solution This will be now in the liquid phase. The reference will be the chemical potential of the solvent when pure, and then my activity is simply going to be the mole fraction of that solvent. Okay, so rewriting that expression, we're going to find that mu of A is going to be equal to mu of A. This is all in the liquid phase when pure, plus RT natural log of X sub A, the mole fraction of A, and again all of this is in the liquid phase. Okay, we're examining how the chemical potential of A changes when we add some solute to that mixture. Okay, so putting this in terms of the concentration of solute, what I get is the following: mu sub A star of the liquid plus RT natural log of 1 minus X sub B. Binary mixture, you only have A and B, so the mole fraction of A has to be 1 minus X sub B. Right, so what do we learn here? Notice that this parenthesis is going to be a number that is always between 0 and 1, which makes this natural log negative. Okay, so all of this correction is going to be negative, and then what I have right here is that the chemical potential when I mix some solute is going to be smaller than the chemical potential of the liquid when pure. Returning to this graph, what we have right here is the chemical potential of the liquid when pure, before we add any solute. Okay, so that is the line of mu sub A when pure in the liquid phase. Now, when we add some solute, what will happen is that, well, this chemical potential is going to be smaller. The Gibbs energy will drop, and we can write this line as a line that is going to be below. Okay, and how below this line is only a function of the amount of solute that you have, not on the type of solute that you have. Okay, so notice that the freezing points have changed and the boiling points have changed, right? So the new boiling point is going to be here. That is my new boiling point. And the new freezing point is going to be here. It's my new freezing point. Okay, so clearly the addition of a solute to a solvent elevates the boiling point and depresses the freezing point. This happens for any solvent. There's no distinction between water or any other substance. All solvents exhibit this trend. Okay? Something that is interesting here is to see that the way that we have drawn this graph seems to imply that the change to the boiling point is a little bit smaller than the change to the freezing point, and that is correct. And we will see how that works out in numerical problems. The final question that we ask here is, can we predict what the changes quantitatively to those freezing points and boiling points are? And the answer is yes. There's some equations that allow us to predict how those changes to the freezing point and the boiling point are. Okay, so the equations that we're going to be using are as follows. The change to the freezing point is going to be equal to a constant times the molality of the solution. Okay, the change to the freezing point is going to be something that we call a cryoscopic constant times the molality of the solution. And the change to the boiling point is going to be another constant times the molality of the solution. Okay, change to the boiling point is going to be equal to the ebullioscopic constant multiplied by the molality of the solution. Again, something that you have to be careful when you utilize these expressions. You have to be careful about the fact that this is going to be a depression, so the freezing point, the new freezing point is going to be lower than the original freezing point, but that is going to be an elevation. Okay, so the new boiling point should be higher than the boiling point of the pure solvent. Okay, again, that's a colligative property, because again, the change to the freezing point only depends on the concentration of the solute, not on the nature of the solute.